of Griffin.
In order to get passes for the park, they could just maybe do like labor for an hour.
No, that's legit a good idea.
Yeah.
If you could volunteer your time to go and like do something that benefits the area, and then you could earn a pass. That's actually a great idea.
Park points.
First
of all, I thought you didn't believe in it.
I don't believe in labor.
Think about
No, Julia.
all of the
I don't believe in people being exploited for their labor. That's labor exploitation. Okay, guys. I'm a little out of order here. Sorry. We're gonna finish up this energy stuff, and there's a couple. I hope you'll find them neato burrito. It actually won't take very long, I don't think. Did anyone figure out 24? The geostationary orbit. Anyone figure out how fast? Okay. So let's look at, we finished 25, so let's look at 26. No one got that figured out?
I didn't even try it also.
Yeah, no. I did problems at 5, 10, 3.
Okay. So 26, let's look at 26 together. Okay, it's got sort of a, it's got an interesting result. So 26 says if you release a rock of mass little m, it's initially a distance of d from the surface of a planet. So let's say this planet, the planet you'd assume is much larger than the rock. Okay. And so the planet has a radius of r and a mass of big M. And the question is, how fast would the rock be traveling when he hits the surface? So, this model here would be maybe talking about, predicting how fast would a meteor be traveling when it hits your planet. And of course, in this simplified version, it's going to start at rest, which is, not the case. But anyway, it gives us a sense of how does this value affect the final answer, and this value as well. Okay, so how do we set it up? Or what principle are we going to use? You guys can answer that one. What? Conservation of energy, which yes involves gravitational potential. So you're going to say the total energy, the initial energy is equal to the final energy. Okay? So the initial energy would just be, well, no one's moving originally. The system's at rest. And so the initial energy would just be the gravitational potential energy. So that would be negative G times big M times little m over what's going to be down there? Close with the second one. It's the distance between their center of masses. Now we're assuming this guy is small. He's just a rock compared to a planet. So you'd say, okay, the total distance. Now, whereas a planet, his radius should be big enough that we have to consider this distance. So the distance between their center of masses would be d plus r. Not squared, not for energy. Remember, the force is gmm over r squared. Energy is negative gmm over r. When I say r, I mean the distance. So in this case, it's the surface to rock distance plus the surface to center of mass distance of the planet. And then what's the final energy of the system? When he gets here. First he's got the kinetic energy plus there's still potential energy in the system here, right? Just with R. Because when he gets here, the energy is going to be negative G M over R. Hello? You know you're supposed to leave?
Yeah.
Okay.
Yeah.
What a world we live in. They send,
Society.
we live in a society. They send the guy to bring me a ticket that tells you. We do be living in a society, right, Emily?
Yeah.
What if Trenton's watching? Trenton, if you're watching this, I just want you to know that you are a lit savage and we love you. Huh? It says 2 people. And by 2, I mean 2 million Twitch fans. So.
Wait, can they like leave chats and tell us who they are?
They could leave, they could chat, they could put a chat in, put a chat.
Tell us.
No, one person left.
Yeah. Yeah. Try to get.
Trenton! Trenton just caught, he, thanks for the 100 bits, bro. I don't know why I'm about to type, I can just talk to him. Trenton, wow, what a savage. He said lit savage present. Thanks, Trenton. Okay, so anyway, the question was how fast. So the first thing you notice, look at all the little m's. They're going to cancel out. And you're going to end up with, let's add this guy over to the left-hand side. And you have G M over R minus G M over D plus R equals 1/2 B squared. And if you will permit me, I'm feeling, I kind of want to pull out a common factor here. Like they both have a GM, right? So I can pull out this GM and leave behind, good morning.
Is Hannah here?
Nope.
Okay.
Does that make sense how I just manipulated the left-hand side? That's good. I didn't do my attendance. Mr. Thompson. Always reminding me. No questions on that last step there? Okay. And then, so the last 2 steps, we can do that in one step, right? To solve for V, we're going to double both sides and then square root it. That's a pretty complicated formula, but there's something interesting here, though, that you've been thinking winky about. Let's see if anyone can figure it out. Something that would kind of break the laws of reality, if you start to think about it.
I don't know if I want to think about that.
So the question would be, what if the planet was, say the same mass, what if it was really small, really dense? What would happen?
Trying to square root
No, assuming D is positive, this number is always smaller than this number, but this is the right region to be looking at. What would happen if, for example, what if we took the Earth? You know, a meteor could hit Earth, right? But what if the Earth was really small? Let's say the Earth was like this big, but all the same amount of mass. How would that affect the V value if R was really small? It would greatly increase V, right? So do you guys see what I'm talking about? Like theoretically, as the radius of the planet approaches 0, what does the velocity approach? Infinity. Which is not possible, right?
Whoa.
Do you guys know the speed limit of the universe? The speed of light. You can't go faster than speed 300 million meters per second or 300,000 kilometers per second. You can't go faster. Light goes that fast, and things like gravitational waves go that fast, but matter can only approach that speed. So clearly there's something going on. Well, obviously no planet's going to really have anything close to having a 0 radius, but you could talk about something like a black hole. If all that mass was concentrated really tiny, what's happening with like things that are approaching it or going into it?
That's what I was thinking about, is like the attraction that black holes have.
Yeah, so you get this is one of the results where you start to think about, well, what happened, because you can show how like, okay, well, based on how strong gravity is, at a certain point, if there's enough mass, what they show is that theoretically it could just keep crunching down smaller and smaller. And so because like a star, there's like a pressure pushing outward. Because think about a star, a star is right, all this mass, all these mass particles, and all the mass particles are attracting each other. So what they really would like to do is all just crunch in, but there's like a pressure created by the processes of the fusion and stuff in the star, this pressure that keeps it in equilibrium, and eventually that fusion starts to die off, and that pressure decreases, and then the gravity wins the fight, and it all, assuming if it's big enough, the star has to have enough mass for this to happen, and then it'll collapse in. So there's a certain amount of mass where it'll crunch down into a smaller star, but at a certain point, if there's enough mass, it'll just keep there's so much mass that the gravity wins out the battle, and it just goes to a black hole. That'd be the theory of how they form, generally speaking. Anyway, and then for a case like of our Earth, the battle is between electromagnetism. Well, the same thing is happening here, but on our Earth, right, the molecules that make up the Earth, the core and the mantle and the crust, they don't want to be close to each other because they have electric charge, right? And so it's like that thing I was talking about the other day when I punched the wall.
Yeah.
It's the electrons being like, bro, I don't want to be next to those other electrons. So, but our Earth has hit equilibrium where, okay, the gravity is pulling everything in, but then the electromagnetic force of the molecules popping each other balances out. So anyway, then you can do the same kind of analysis for something like Jupiter, like a gas giant, same kind of thing. Okay, anyway, moving on. So let's discuss 27. Are you guys still okay with that idea I talked about yesterday where we still have, this formula of, let's actually go back a second. Erase this. Simplified version. What I'm trying to say is, as something moves farther from Earth, what happens to the gravitational potential energy? It gets bigger. So if this is an object, and this distance is r, the gravitational potential energy is negative gm over r. And so as r gets bigger, this value gets closer to 0, but it's negative, so it's actually increasing. And again, if you graph the potential energy versus radius, or radial distance, it looks like this. So as you move to the right, as you increase the R value, you're actually increasing the potential energy. Does that all make sense? It's a little bit of vocabulary. increasing the potential energy of what? So before, we used to talk about the block having potential energy, but technically, it's actually the potential energy of the system. Notice the formula has two masses in it. So we typically omit this at the beginning because it's more confusing than just to say, oh, the block MGH, goes up, goes down. The real idea is that, as this moves up, the system increases its amount of potential energy. And I hope that makes sense, because if you release that block and let it crash into the planet, the farther away you release it from, the faster it's going to crash in, the more energy there's going to be, right? So 27 says a cannon launches a cannonball straight into the air. So let's describe what happens as the ball is traveling upward. So here's the cannonball. As the ball is traveling upward, what's happening to the gravitational potential energy? I don't know, I said equals, sorry. This value is increasing. What's happening to the kinetic energy? It is, as you're traveling up, you're slowing down, right? At least if you're in the gravitational field of the planet. So your kinetic energy is decreasing. And then here's some more vocabulary. Total mechanical energy. That just means the sum of those.
So would it be the same?
Now, we wouldn't say it's zero. We would just say it stays the same, or it's conserved.
Because as you lose kinetic, you gain potential.
So you're probably thinking of this. The change in energy is zero. Right? There's no net change as this is happening. So if the cannonball, say, loses 10 joules of energy between two moments in time, that means the gravitational potential energy of the planet ball system must have increased by 10 joules. Right? As it's coming down, the gravitational potential energy is decreasing as the kinetic energy increases, and the total energy is conserved. And of course, when is the potential energy of the cannonball Earth system at a maximum? The apotheosis.
Precisely.
That's a good word. At the peak. Now a nicer answer maybe is this is at a max when the kinetic energy is at a min, which would correspond to the peak of the trajectory, which also corresponds to the velocity equal to zero. That kind of tells you the whole picture, right? That kind of puts it all together, right? All right. Sorry, guys, we're almost done. Just got a couple more things. You guys ever seen that movie Ferris Bueller?
Yeah.
And the teacher, it's not Ben Stiller, it's Ben Stein.
Ben Stein. I watched a documentary with him in it last night, actually.
Oh God, I think I know the one you're talking about. No, Julia, no.
Have you seen it?
I don't think I can sit through that.
It's so good.
What documentary is this?
Basically he goes around to all of these biologists. What, Mr. Hall?
Sorry.
Oh my God.
Go ahead, Julia. I'm sorry.
No,
We'll keep it inside.
He talks to all of these prominent evolutionists like Richard Dawkins, and he kind of just argues with them about stuff.
Fair enough.
It's really good.
That guy sounded really annoying.
Mr. Hall.
Okay. Here's a star. No, if you don't know who that is. If any of you guys know what this is, I'll be impressed. From one of the greatest shows of all time, Beavis and Butthead. Anyway. Cornholio, yeah. Anyway. That character in the movies, he's the teacher, he talks like this. We have a star. This is an elliptical path for the comet. Okay. So comets will travel in an elliptical path where the sun or the star it's orbiting, not just comets, literally everything, like Earth does as well, Jupiter, Pluto. Comets just happen to have these more interesting, like very eccentric orbits. Eccentric just meaning how like stretched out it is. A circle has zero eccentricity. So anyway, or is it an eccentricity of 1? Anyway, it's a mathematical definition. It's not really relevant for this. But so as the comet travels around, let's say he's traveling counterclockwise, and let's say he's like here, and he's traveling. Of course, his velocity is tangential to the path. All that stuff we've been talking about forever. Oh, it says traveling away. So, well, there's 2 questions here. They've got to consider both cases. So let's say, same orbit. So he's traveling around this ellipse. Oh, and by the way, it's an elliptical orbit with the star at the focus of the orbit. But if you really want to, make friends and impress people, you say, you say, actually, the sun and the comet are both orbiting their center of mass, actually. And then everyone's like, wow, thank you. Thank you for correcting me. That's what happens in real life, IRLs. So, yes. Anyway, so you can try that out.
I will.
Yeah. Just using basic, I don't know, like, there's a lot of ways you could think about this. For one, what direction is the force on the comet when he's here? Please tell me, this one.
Yeah.
Mr. Star pulls on him, right? So if I put it in red, right here, the force points that way. So is that going to slow him down or speed him up? It's going to slow him down. So here he's slowing down. Whereas here, the force points this way. That force tends to point in the same direction as the velocity. He's going to speed up. Okay? So that force vector is actually doing 2 things. It's one, some of it's speeding him up. So there's a component of that force. Actually, I'll draw it up. It's kind of interesting. There's part of that force vector is pointing along there to speed him up, but there's also a component that's perpendicular that's keeping him in that curved path. It's actually changing his direction. So 2 things are happening. Speeding up and changing direction. Same thing here. There's a component slowing him down, and there's a component changing his direction. Okay? So velocity is decreasing. How about the gravitational potential energy? What's happening to that? Yeah, so back to this. This is number 28 is this one, 29 is this one. So the velocity is decreasing, sorry. Potential energy is increasing, which of course goes along with kinetic energy decreasing. And then of course the total energy is doing what? Stays the same. We all comfortable with that?
Yeah.
Okay, so 29 should be fairly obvious. It's just the reverse of that. Let's look at 30. And then we just got to do a little bit of let me just mention this because I want you to do 31 on your own. It's kind of just a rehashing of this. But think about angular momentum. So suppose this would be a little bit of a convoluted question, but suppose you had a question that said, explain why this is happening using only angular momentum. Like you can't use energy, you can't use forces. You have to just purely talk about angular momentum. What would you say for something like that? Anyone.
Going away.
Sure, for this moment, what does angular momentum have to do with this thing slowing down? What's decreasing?
Yeah, so.
What?
Yeah,
Say the question again, don't get it, I promise. If I don't promise.
The question is what does angular momentum tell us about why the velocity decreases here and increases here?
Angular momentum conserved.
Oh, thank you. Thank you.
I thought it was more than that.
The angular momentum of the, well, that's half of it. You start with core concept, right? The angular momentum of the system would be conserved because is anyone coming from outside that system and exerting a torque on the system? Nope. So you'd say, first you'd start with angular momentum of the star comet system is conserved. And what's the formula for angular momentum?
Oh, equals. Oh. No. Yeah.
Okay. So, if you were saying something like, oh, he's moving from here to here, okay, which of these, well, I guess both are changing, but if this is conserved, as you move away from the star, what are you doing to this number?
It's gonna be.
It's increasing it. Well, why? Because I for a system is the sum of all the mr squareds. So if you increase the distance if you increase the r value, which you clearly doing, right? As you move away, you're increasing that distance. So when you increase the moment of inertia of the system, you would have to then decrease omega, this angular speed, in order to keep this the same, to conserve. Make sense?
Yeah.
Hello, Jesse. How are you?
Is this physics?
Yes, it is.
Oh, I miss physics. Yeah.
Thanks, Jesse.
Oh.
Okay. Let's look at we have time to do. We gotta do 30, and then I'll have enough time to go over escape velocity. You guys ever heard of escape velocity?
Yeah.
So number 30. This is just an exercise in precise language. Okay. As a block slides down a ramp, is the total mechanical energy of the block changing? The answer is yes. Is the total energy of the block Earth system changing? No. See why that's a tricky question, right?
Yeah.
Because this requires a shift in perspective, and I'm well aware that earlier in the year we talked about, well, wait a second, you said, okay, the block, right, mgh turns into 1/2 mv squared. That's a conservation of energy argument. Yes, it is. But if you want to be very precise, that was a local, well, to be very precise, you can't just, the block itself, by itself, does not have the relevant gravitational potential energy. So it's the block and the Earth together. Does that make sense? If there's no Earth, there's no gravity, so there's no potential energy. So I hope that makes sense. So for this one, the total mechanical energy of the block is increasing. Because if you're just looking at the block's total mechanical energy is just its kinetic energy, 1/2 mv squared. That's clearly increasing as it goes down the road, right? But if you are looking at the block and the Earth together, then you'd have to say that, well, now it's potential energy plus kinetic energy. So the total mechanical energy of the system is conserved. Okay? That one might not, that might be confusing right now. It's fine if it's confusing. You have to just kind of think about, again, it just has to do with the fact that if you can't have gravitational potential energy without like a planet or something there providing that gravitational field. So anyway, so just ultra clarification for 30, the answers are, the true ones are A and F. Okay, escape velocity. So 32, just read 32 while I'm erasing here.
So hold on, it says never come back. That just means like you can go into orbit. It's not going to come back to the atmosphere anytime soon, right?
Well, orbit, no, because you have not escaped the gravitational field if you're trapped in an orbit.
Because in an orbit, you want the gravitational field to stay in orbit, where the escape velocity, you're going to get out of the entire system.
A lot of times they'll visualize a gravitational field as like a well, like this. Now, ideally, it's a three-dimensional, well, it's a two-dimensional surface in a three-dimensional space. But this is a one-dimensional surface in a two-dimensional space. But where this depression is the warping of space-time by the presence of like a star. And so, or say it's a planet. Let's say it's Earth. This could be you. Well, usually when you jump, you go up, but then you come back down to the bottom of the well. Makes sense? And so an orbit, if you can imagine this big thing being like a three-dimensional depression, an orbit is you kind of rolling around at some distance away. This is you on the Earth's surface, but if you were, it would be like an orbit like this. Again, you have to imagine this being a three-dimensional surface, but does that make sense?
Yeah.
In calculus, if we revolve this around the y-axis, that structure. Anyway.
Remember that one you where it had like all the Mars' mass and Earth's mass, and Sun's mass, and then it had like this one like that was obviously more massive than all the other ones. Like it had some roast in it. Like
A what?
like your mom, like is heavier than all of them.
Wow, epic joke. That is so savage. Okay, so here's the idea.
The room is in tears.
Oh, and so Aaron, the escape velocity. Sorry, I didn't really finish the thought here. The escape velocity would be you fully escaping the well.
Okay, I got you.
Now, if you shoot out of there with some incredible velocity, yeah, you could just be like, pew. But we're saying, what's the minimum velocity? Which would mean that you barely make it out and have like a really small velocity as you escape the field. Okay, so what you do is you say, here's the planet. Here's the surface at a radius of r. The planet's mass is m. Here's the cannonball. It is shot up. Well, mass of little m. Can we predict what's going to happen to little m? Okay, let's shoot this thing out. And there's a hint in there that says, well, if you did the minimum velocity that escapes the planet, what would happen is as your distance approaches infinity, so as your distance from the planet approaches infinity, your velocity would be approaching 0. Does that make sense? Yeah, okay. And then what would the potential energy be? Gravitational potential energy would be approaching 0 because look at the formula. If that R is enormous, it's going to be approaching 0. Which is really weird because it's technically increasing towards 0. If you think about it, I'm just like, what? Anyway, it's negative. Okay, so total energy argument. Right here, he's got total energy of gravitational energy plus his kinetic energy, right? This is him getting launched out of the cannon. But wait a second. Conservation of energy, later on, what's his potential energy? What's his kinetic energy going to be? So the total energy over here is just 0 plus 0. So you can kind of rephrase this question as, how fast do you have to launch the cannonball so that its total mechanical energy is 0? Which again, it's kind of weird to think about, right? It all comes back to this, defining this as a negative number. So anyway, let's solve it. Add him over. Well, first thing, what can we can divide both sides by little m, right? Add him over, so you get 1/2 v squared equals gm over r. Double both sides and take a square root, and you get the famous formula. That's nice. By the way, look familiar to you? That's all? No. It looks a lot like those orbit equations, right? Phrased differently, this one is, you take it into context, this R represents the radius of the planet, M represents the mass of the planet, whereas in the orbit, with that orbit problem, you treated this, this planet as a point mass, and R represented the orbital radius, and V represented the orbital velocity. You had this relationship, right? So kind of curious how there's that connection between the two, even though they're talking about pretty different things. In fact, we didn't even use energy at all to derive this. This didn't involve energy. It's just purely, this is derived from centripetal force and Newton's force formula. Anyway, I wanted to do the black hole question with you. So on 33, you're going to calculate what's the escape velocity on the moon. Okay. Which will, I don't know, you ever wondered if you went to the moon and could you shoot a gun on the moon without oxygen? I want to say it would work, right?
I'm not sure what happened if you shot a gun in space.
I don't know if it would. I feel like there's maybe enough oxygen. Well, I don't know. Someone can maybe figure that question out. I want
spacesuit for your gun. Would you?
That would definitely help put it in a Ziploc bag full of air if that was, because that'd be my only concern is with, but I think the gunpowder will still ignite and be fine.
In the hit TV show Firefly by Joss Whedon, in one of the episodes, Jane, he had to put like a bag over his gun to shoot it at that one shirt. And Firefly probably knows.
Okay. All right. So last question I'll do with you guys on this. If you've ever heard of a black hole, here's the main idea behind it. The idea is suppose you had a whole bunch of mass. Lie down. Suppose you had a whole bunch of mass, big M. This is number 35. Suppose you had a whole bunch of mass that, like I was talking about earlier, gravity has won the battle. All that mass has collapsed down into a super small area. So imagine the mass of the sun collapsed down into like something this big, or a thimble, or like a peanut or something. I believe theoretically it's even smaller than that. It's theoretically 0 volume, which is weird to think about. But anyway, it actually still works out fine with a thimble, or something the size of a ping pong ball or something. So what we're going to do is say, suppose there was some theoretical radius, we call this r, some distance from all the mass. Remember, this is a super dense mass. And suppose that from this location, the escape velocity was the speed of light. $300 million meters per second. So do you understand the setup here of like what we're, the concept?
Not entirely.
Okay, so it's, suppose there was, we just derived a formula for escape velocity, right? And you guys see the bigger the mass, the bigger the escape velocity. So on a very heavy planet, like a very, well, it also depends on the radius too, right? So a very dense planet, like if a lot of mass is in a kind of a small volume, the escape velocity is going to be big. Whereas if it's a planet with not very much mass, or if it's kind of big, has a big radius, then the escape velocity is going to tend to be kind of smaller. What I'm saying here is imagine the densest object you can think of, where all the mass is so concentrated that, and then you talk about this sort of like, just sort of a pretend surface. So what if you were standing here and you had to travel the speed of light to escape the gravity? So what would happen here if you were inside the circle? You'd never be able to escape because nothing can travel faster than the speed of light, right? So the question is, well, we just derived a formula. The formula we just derived says V equals the square root of 2gm over r, right? What V we just said, what if we wanted the V to be what? The speed of light, c. I'm just gonna use the letter c, speed of light. Okay, well, what's the math say? Square both sides. And then solve for the r. Do we understand that, or?
Yeah.
So what does this say? This says that I could, in theory, calculate, give me a mass, give me the mass of the star you want me to consider, and all I got to do is multiply 2 times g times the mass of the star, and then divide it by the square of the speed of light, so 300 million squared, and that would tell me this radius. Well, actually, it's a small number, right?
But the speed of light squared is big ass.
Yes, so dividing by that huge number. Also, you're multiplying the mass by that really tiny number and then also dividing by a big number. So I gave you one to try out, like the sun. Imagine you collapse the sun down into a thimble, just plug in the numbers, and that'll tell you that if the sun were to crunch down that small, what's the radius at which, it's called an event horizon. So what's the radius at which the escape velocity would be the speed of light, and so within that radius, you'd be trapped forever. Black hole. See ya.